All right, let's talk about the ionic basis of a contractile cell. So now contractile cells are not autorhythmic. They are going to rely on calcium. They're going to rely on the action potential being propagated from a pacemaker cell, right? This is going to be where gap junctions are important. So a pacemaker cell fires an action potential, and it's going to communicate that electrical impulse via a gap junction over to a contractile cell, and then we'll have these events occurring. So I want you to bear that in mind here. Contractile cells are not autorhythmic. They do not spontaneously depolarize. They rely on the opening of voltage-gated calcium channels. They rely on the movement of calcium to trigger excitation contraction coupling. Okay. So let's speak about the ionic basis of a contractile cell. Okay, so very similarly with a contractile cell, we have threshold at about -50 or so, let's say -55, but then resting is going to be slightly more negative simply because we have more potassium channels on contractile cells. So the ionic basis for these two cells differ because there's different amounts of ion channels on these two cells. So we have more potassium channels here, and so the membrane is going to be at rest a little bit more negative than it was for a pacemaker cell, so -90 here. Okay. Now the phases here are going to start with phase 4, rapidly upstroke. Okay, so we'll start with phase 4, move to phase 1. Running out of colors. Okay, so these are our 4 phases, and we start with phase 4, which is at rest. Okay, so phase 4, which is at rest, what we have is that the membrane is at complete rest, and what we see is that there's an increased permeability for sodium, for potassium, and decreased permeability for sodium and calcium, meaning that the membrane potential is closer to the equilibrium potential of potassium, which is very negative. Okay, and that's how we start off here. The first thing that happens is we have opening of sodium channels. Okay, and that's going to give us the upstroke here, the rapid depolarization, which leads to an action potential. we have increase in the permeability to sodium. So sodium's moving, sodium channels are open, and we rapidly depolarize the membrane. We fire an action potential. But that's not where this ends, okay? That's not where this process ends. We then close those sodium channels. So the second step here is closing of those same sodium channels, which decreases the membrane permeability for sodium. Okay. Now, because we still have some potassium moving here, the membrane potential is going to try to repolarize. And so what we do in the third step, which is called the plateau phase, is we then close those potassium channels. What we're trying to do is we're trying to interrupt repolarization. All right? If we would allow this process to continue, the cell would completely repolarize, and we don't want that. We want some time for calcium to enter the cell, and we need calcium for two reasons. We need calcium to allow muscle contraction. Okay, we have that same sarcomere structure here in cardiac muscle. Calcium is going to interact with troponin, and it's going to bring about cross-bridge cycling, which is allowing that muscle to contract. So we have to have a brief period of interrupting this cell from repolarizing. And this is called the plateau phase. Okay, and what happens in the plateau phase is that we decrease the membrane permeability to potassium. So we close those potassium channels to stop the membrane from repolarizing. And then we open up some calcium channels. Okay, this is going to allow calcium to come in, calcium to interact with actin and myosin, and allow that muscle to contract. Okay. And then the final phase here is that we allow that repolarization to continue by reversing these channels. So now we open up those potassium channels and we close those calcium channels once again. Okay. And we're going to repolarize the membrane right back to -90, which is at rest. Okay, so let's go over that one more time. We start off at rest. We open up sodium channels first. That causes sodium to rush in. The membrane depolarizes. We fire an action potential. We then close those sodium channels, but we still have the movement of potassium at this point. And so if potassium is moving, it's going to be going out of the cell. That's where its electrical gradient is. It's going to be moving out, and so the membrane is going to start repolarizing. So in order to stop the membrane from repolarizing, we then close those potassium channels, and we open up calcium channels here in the plateau phase to allow calcium to enter the cytoplasm and allow excitation contraction coupling, which brings about muscle contraction. When that is over, we can then close those calcium channels. We have enough calcium at this point. We can open up the potassium channels and allow the membrane to continue repolarizing. And that is the ionic movement of a contractile cell. Okay, so two important distinctions or two important differences you want to remember for the contractile cells is that, one, they're not autorhythmic, so they do not spontaneously depolarize. They have to receive electrical input from the cells around them, so from the pacemaker cells via gap junctions. Two is that the purpose of calcium in these cells is not just to change the membrane potential. The purpose of calcium here is to interact with actin and myosin to bring about muscle contraction. Okay, alrighty. Any questions on that? Okay, so once again, here are those steps listed from phase 1 to phase 4. And you want to practice drawing these out. Again, make sure you understand them. Make sure you can differentiate the contractile cell, how the ions move there, from the pacemaker cell, how the ions move there. All right, again, this is a representation of that. Okay, now we're going to move on to talk about what happens when that calcium comes into the cytoplasm. How does calcium bring about muscle contraction in cardiac muscle? So excitation, contraction, coupling specific to cardiac muscle. Okay, that's what we're going to talk about now. So we've seen this process before. Calcium comes in, it binds to troponin, it moves tropomyosin out of the way, and it brings about phosphorus cycling. So that process is something we're familiar with, and it's very similar in cardiac muscle. Okay. Two differences here, though, are the presence of gap junctions. So there are no gap junctions in skeletal muscle, but there is in cardiac muscle, as well as the source of calcium. So just like we saw with smooth muscle, calcium is not only coming from the storage in the sarcoplasmic reticulum, it's also coming from outside of the cell, so the extracellular environment. So those are the two differences between excitation, contraction, coupling in cardiac muscle. So let's walk through these steps here. An action potential is fired in an autorhythmic cell. It's propagated to a gap junction to a contractile cell, okay? Or it can come from another contractile cell. So the action potential arrives at this cell from that gap junction. It travels down the T-tubules, and then it ends up at the sarcoplasmic reticulum, where we have these voltage-gated calcium channels. Now, calcium is going to start entering the cytoplasm of the cell, and remember, it's coming from two sources. It's coming from the external environment, and it's coming from the SR. The SR is drawn in blue here. All right, so calcium is released from the SR, and then it floods the cytoplasm. The third step here, calcium binds to troponin. Again, this should be something we're very familiar with. Calcium binds to troponin. This moves tropomyosin out of the way. It uncovers those binding sites. The myosin head can interact with the binding site on actin, and this brings about phosphorus cycling. All right, so we have phosphorus cycling happening here. And then when the cell is ready to contract, when that signal is over, when the membrane is no longer depolarized, when it starts to repolarize, what we have is calcium leaving the cytoplasm. This is something you should also be very familiar with. In order to cease muscle contraction, calcium has to leave the cytoplasm. So calcium is going to leave the cytoplasm via three routes. It can be actively pumped back into the sarcoplasmic reticulum via calcium ATPase pumps. So you have a calcium ATP pump right here that's pumping calcium back into the SR. It can be exchanged at the surface, right, for sodium. So we can use the sodium exchanger to bring 3 sodium in, right? Sodium is going to be moving along its gradient, and use that energy to carry calcium against its gradient. We should know that method of transport by now, right? So we have the exchange of sodium for calcium, or we have calcium pumps on the membrane as well, the sarcoplasm membrane. All right, so those are the 3 routes of allowing calcium to leave the cytoplasm. Put it back into the SR, exchange it for sodium, or just pump it out of the cell back into the extracellular environment. All right. Okay, and then this slide pretty much summarizes those 3 methods as well. Those 2 calcium pumps, one on the SR, one on the plasma membrane, and then the sodium calcium exchange.